So that's where we're going. Okay? So today I'm going to do subdivision. I'm going to finish it up. And I'm going to start with a slightly different one today, and this is going to go into what we call Catmull-Clark. This will go into what we call Catmull-Clark subdivision, which is what most people use these days, some variant of Catmull-Clark subdivision. There's also one called loop subdivision. I'll wave my hands at this one. This works on only triangles. Which is, if everything's triangles, it's actually a little bit easier. In some sense, the data structures are a little bit easier if everything's triangles. But with Catmull-Clark, you have to do the same thing as I did last week with Due-Sabin subdivision, is that with Catmull-Clark, you have this, the data structure from hell. You have pointer hell data structure, and everything has to work that way. So I'll wave my hand at this one, and then you can see afterwards that you could probably, it's pretty easy to invent your own subdivision technique. It actually, all the subdivision techniques really do is what we call split and smooth things, and you can invent your own after that, and many people have. These tend to be based on a little bit more mathematics as we go along. Okay, so here we go. Suppose I have a curve like this. There's something called Chaikin's curve. Which looks kind of like, if you remember, oops, no, it doesn't do this. It goes 1/4, 3/4, and you connect the dots like this, okay? You connect the dots like this to get a new one. The one I'm going to discuss today is slightly different. And let's see, what happens with Chaikin's curve, if you remember, we get these pieces that look like parabolas. Okay, it turns out it's two parabolas pieced together. And people started saying, well, these parabolas aren't very nice, and I've gone over this before, because you can't get inflection points. Right? In general, you can only get them at these these points here where they join. You can only get them at where they join. And what would happen if we actually used a cubic one instead? Okay, we used a cubic one instead. And these things tend to be, if you remember, these things tend to be like Bezier, little Bezier curves. What would happen if they made it out of cubic Bezier curves? And the procedure that comes out is actually quite simple. It looks like this. That you use the midpoints here, okay? And then, so these 4 points come into 1, 2, 3 here, 4, and 5. 5. There are these extra points in here, and what happens is that these points, you connect up this segment, like this, to get 5, okay? And then you do it again. Started with 4, and you get 5, and then you do it again, and you say, well, you do it again? Well, what you do is you do it first with these 4, again, and then you do it with these 4. Okay? Now it looks kind of funny this way. And we break this into, we actually break this subdivision procedure into these two things where we have these points here, which are called edge points. Okay, which are just the midpoints of these segments, and we have these points here, which are called the vertex points. And so, given a huge thing, like this, like this, given a huge thing like this, we can specify these points by first specifying all the midpoints. These are the edge points. Like this. Then specifying these vertex points, and I'll show you how to calculate the vertex points in a second. They're actually pretty easy. And then connecting the dots out. Like this, into a new curve, and then doing it again. So edge points and vertex points. And how do you calculate the vertex points? It turns out it's pretty easy. That if you have these 3 points here, there's 2 edge points, one here and one here. Okay? If you take halfway between this edge point and the vertex, halfway between here, draw a line like this. Halfway between here is the vertex point. So it's halfway, halfway, halfway to get the vertex point. And if you remember, the halfway, halfway, halfway looks remarkably like Bezier curves, right, that we did. Okay, it looks remarkably like the Bezier curves. And so once you get this curve here, you can do it again. And do it again, and do it again, and do it again. And it turns out that if you have these points here, P0, let's start with 0, P1 and P2, and here's E0 and E1, right, 2 edge points. Then, let's see, E0 is equal to P1 plus P2 over 2, okay, it's the midpoint. E1, oops, let me try again, P0 plus P1 over 2. E1 is P1 plus P2 over 2. And the vertex here is equal to P0 plus 6P1 plus P2 all over 8. Okay, turns out over 8. You have to take a yellow sheet of paper to run this out to figure out it's really this, which is, I think it's P0 plus P1 over 2, which is, I don't know if I should write this down or not. Okay, it's E0 plus P1 over 2 plus E1 plus P1 over 2. Take the midpoint of those guys. Okay? And this, it turns out, is actually a nice way of doing things because they're kind of points here. The vertex points here correspond to one of the original vertices. Okay? And if I did this again and had edge points and vertex points, I'd get another vertex point right here if I did it again, and another vertex point next time through. And so each time we have a vertex, we have a set of points that correspond to it. And the nice thing about this is that this is another course that we would do, but you can actually find out where these things go in the limit. Okay, and you can actually write that down fairly quickly, where these things go in the limit. And but this is a scheme that actually does this very, very nicely. So there's vertex points and there's edge points in the scheme. Okay, and you can generate a curve. The curve turns out to be cubic. It turns out to, well, if you can see here, what happens is this point, it shrinks considerably. All right. This point moves up to here, which then moves to here, which then moves to here. And what you get is a curve in here somewhat like this. Okay, this one shrinks considerably, but it actually can end up inside. Okay, it ends up inside. It has all the properties that the Bezier curve did and everything else. Okay, can you all see how this shrinks quite a bit and ends up in here? Okay, that it actually shrinks fairly substantially in here. But it works out pretty well. Now you can take this curve, which is a Chaikin's curve lifted up. This is I'll just call this a cubic curve. you can take this and lift it up to a surface. Okay, so, and these surfaces are called Catmull-Clark. And Catmull and Clark did this when they were graduate students, both at the University of Utah. So this was kind of a paper that they wrote. They published it in a really obscure place, right, which all of us now have a copy of this book on our shelves because it's the only place we can find this paper. But it actually was pretty simple. And if you draw out a 4x4 array of points, it's not too hard to see how this is going to work. And this is really a three-dimensional thing coming out at you. This grid. It's really a three-dimensional thing coming out at you. And what you do is you do the same thing as we did with Chaikin's to get what we call Du-Sabin. You do this subdivision procedure along all these rows, and then you take the resulting thing and you do the subdivision procedure along all the columns. Okay? And so if you do this, you start with these edge points, and let me label them here. The edge points and vertex points. Okay? Edge points and vertex points. And it doesn't matter really how big this big square matrix is, but you get all these edge points and vertex points by doing it along the rows, and then you do the same thing along these guys, right, to get columns. So you do an edge point in here, okay, to, how am I going to do this? 1, 2, 3, 4. Let's call this E prime, right? There's an edge point. Let me connect these up. Right? As if this were the 4 points, you would get another edge point here. Okay? I'll put circles around them. There you go. Another edge point here, and then you'd get a vertex point here. Okay? Where the edge points are the midpoints halfway between these two E's, and the V's are that E plus 6 times that E over 8. Okay? So you do it all on the same thing, and you get these new edge points here. And these new vertex points right here from these curves going in. Okay? And you get this big mess, all right? You get this big mess. But what you get out here when you're done is if you connect the dots, you get another grid. Okay? And this other grid starts here. Oops. See it? See the other grid emerging? And it's shrunken down from the other one a bit. Okay, it shrinks down, but you get a new thing in here. Okay, and now it looks like a big mess, but all you did was you did that subdivision algorithm all in this direction first, right, calculating edge points and vertex points, and then you took those these things as kind of a new matrix, and you did all the edge point vertex points in the other direction along the columns. And now you can kind of sit down and you can kind of figure out what happened. If you look at one of these points here, okay, where did this come from? Well, it came from the, it turns out it's the there's an edge here that was calculated, a midpoint here, and a midpoint here. And then that's the midpoint here between the two. And this is just the average of all 4 points coming in. So let me draw you another grid here. Smaller. No, I'll do the big one. Like that, okay? So these things in here tend to be what we call face points, right? And the face points tend to be calculated by taking the average of these 4 corners. Okay, that's all they are. So you can run through here and get all the face points. Turns out to be pretty easy. Then you have points that are kind of on the original edges here that were calculated a couple times. And these are called in this new scheme edge points. Okay? And it turns out the edge point is the average here of the 2 face points on either side and the 2 vertices. Okay, it's just the average of these 2. Now notice when I'm taking averages, let's see how to explain this. When I'm taking averages, if I have a hump, these grids in a hump, if I'm taking averages, I'm decreasing this in size, right? I'm replacing points by their average, right? It's actually pulling this thing away from this thing. It's great for taking a square, a cube-like thing and making a parachute out of it, right? It pulls away to get this surface. Okay? And then we have these points here, which were the vertex points. And it turns out the vertex points are a little harder to calculate. But when you do all the math of all this thing, and it takes you several yellow sheets of paper to do, it's actually out there on the web if you want to find it in my notes. But when you do that, you get a new, what we call a new vertex point, okay? And this vertex point is, let's see, well, I guess what I'll do is I'll walk over here and I'll write them down. So you get these face points. F is equal to the average of all points defining the face. You get edge points. E. These are the average of the 2 what? Adjoining faces. And the 2 vertices that define the edge. Finding the edge. So up here you have the face point here, kind of is the average of all 4. Here you have an edge point, a point you get corresponding to the edge, is the average of these 2 vertices and of the 2 faces, right, that are on either side of the edge. And then you have the vertex point, which is equal to this, which is, do I have 4 here? I think so. Which is the average of all face points surrounding the vertex plus the average of all edge points plus some constant times the vertex, original vertex. And this constant, unfortunately, is kind of funky, but the scheme is effectively if you take this little thing here and you look at, oops, I'll draw it on this board. If you look at this vertex point here, it is, to get it, you have all the face points around it, all the edge points around it. Okay, so this is the average of all the face points and the average of all the edge points together, plus a little bit of what's already at that vertex. Okay, you want to have the vertex kind of influence, right, what goes on. And this is this subdivision scheme that everybody does. Okay. Now, it looks kind of weird, but it's not bad at all, because we can do face points, edge points, vertex points. We can just run through all the faces, calculate new face points, run through all of the edges. Once we get the face points, we can get the edge points. Once you get the face points and the edge points and you have the original vertices, you run through it one more time and you get all the other ones. Okay, so 3 passes and you're done. And you can get these surfaces out. Well, after Campbell and Clark calculated this, they kind of they started communicating with these guys in Europe, Dew and Sabin, who had done the previous paper, and Dew and Sabin said, hey, we can do ours for any arbitrary mesh, right? It doesn't have to be rectangular mesh like this. And Campbell and Clark went back and they started looking at things, and they actually wrote it down in the form that we kind of know it today. And it's true, you can do this with any mesh also, okay? Because, look, the face points are the average of however many vertices that surround a face, even if there's 10, right, vertices around it. Face points still the average. Edge points can still be calculated as the average of the 2 vertices defining an edge and the 2 face points. It doesn't matter. Same thing with a vertex point. It doesn't matter. Just take the average of however many are around it. And so you can do this with any scheme. And this is the one that you'll see that people use. And the reason is because you get really cubic mathematical things out of it. Okay? You get cubic mathematical things out of it. And, so when you see up, or when you see, the little guy playing chess or something, you can say, aha, I know how his hands were done, right? They use these surfaces like this. And it's just a really simple thing. Now, this C here causes people problems, and it's really, this C happens to be n minus 3 over n, which is kind of weird, where n is the number of edges coming out from the vertex. Kind of a weird constant to be there. And people started saying, hey, I'll put my own constant in, and we'll play with it, and we'll see what happens. And it turns out that at these, what we called extraordinary points last time, which maybe had 5 things coming out, not 4, right, and things like this, you get different mathematical behavior at these points, depending on what constants you put in here. Okay, and this constant has kind of developed an entire little mathematical subculture, right, trying to figure out what these various constants do to things mathematically. Turns out that if you just forget that constant and you get it 1, then in some points you can get these spikes to come up in your surface, which people don't like too much. Okay, but this is Campbell-Clark, and I just want to make you aware of it. It's the natural extension of all the Dew-Sabin stuff that you did at the beginning of the quarter. Okay? And everybody now uses it. I can take any mesh and I can tell a grade school person, okay, define me all the face points, now define me all the edge points. I mean, the math is easy. It's all averages. Okay? And now define me all the vertex points. I got a new mesh, right? I can do it again. You can describe this procedure to just about anybody. Making up the data structure to do it's another thing, okay, in general. But the procedure is actually fairly nice. And all of us have implementations of this data structure from hell, right, which has pointers running all over the place. We call it a split edge data structure. And we all have copies of this that we use over and over and over again in our work. And if you go into some modeling packages now, Lightweight 3D, Maya, just about anybody has these also, okay, in order to be able to do these things. Let's see. There's some other things. Let's see. How do we model? Let's see. I'll now do the triangle one. quickly. How do we model a sphere in computer graphics? Everything has to be triangles. And you can't fit Bezier patches to a sphere very well. Okay? How do we model a sphere? Well, what we do is we use an icosahedron, okay? Which is a 20-sided regular thing with triangles. I think there's 5 triangles around the North Pole, right, etc. There's 20 triangles on this thing, okay? And it's a regular polyhedra. One of the, I think there's 5 of them, 6 of them. There's the cube, there's the tetrahedron, there's the octagon, there's the dodecahedron, right? Am I missing one? And this one, the icosahedron, okay? Well, what we do with the icosahedron, 20 sides isn't usually enough, right? It makes us a blocky looking sphere, right? So what we do is we make more sides. And what do you do to make more sides? Well, you take each one of these triangles and you split it into 4 pieces, okay? Now, this point right here isn't on the sphere, okay? Turns out, I mean, this is a straight line, right? From these 2 points might be on the sphere, but straight line gets you off the sphere, and so it looks kind of like this. 2 points on the sphere, straight line going off. I want to take the midpoint there, okay? Well, what I do is I just calculate, a point through the center of the sphere, and I lift this point up onto the sphere, okay? It's really easy. I can figure out how far this point is from the center, right? And if it's not the radius, well, I increase it out, right? So it is the radius. So what we do is we subdivide this triangle into 4 pieces and lift each one of these 3 points out to the surface of the sphere. Okay? And we do this for all the triangles. Right? In the sphere. Now we don't have 20 anymore. We now have 80 triangles. Okay? But all the points of the 80 triangles lie on the surface of the sphere. Okay? If 80 isn't enough for us, what we do is do it again. Okay? And split these triangles in this nice 1-to-4 way. Okay? Now you get 320. If that's not enough, you get 1200. Okay? And real quick, you get enough triangles to actually approximate a sphere. And it's actually a pretty easy process to do. The only tricky thing at all is to take each one of these points on a straight line going here and lift it back up to the surface of the sphere. We have to change it somehow, okay, to make it work. And this procedure of taking these triangle meshes and doing a 1-to-4 split, okay, people have moved into the subdivision world, that if you have a triangle mesh any arbitrary triangle mesh, okay, what we can do is we can take do 1-to-4 splits on the triangles like this and get a subdivision procedure which enables us to get a finer and finer approximation. And what we do is we define these points that we take as edge points this time. Okay. Define all these new edge points. I need to go all the way around one here. Like this. And all these edge points are just exactly what you might think they are. They're just the midpoints of the line segments. Okay? And what this subdivision procedure does is something different. It then takes the original point and defines a new vertex there. Okay? And it defines this new vertex by taking the sum of all the edge points. Right? Let's do it this way. edge 1 plus edge 2, right, takes this over n, however many edges there are, plus this vertex, the original, right, and takes some average of these. And it turns out that what people have found out mathematically, which is kind of interesting, is they take 3/8 of the of the average of all the average of all the edge points and 5/8 of the original, and add them together. So if you kind of look at this, if you take the average of all the edge points, it's going to be some other point, right? Here. And then you take a line between these, and you kind of take 5/8 of the way along that line, and that's the new point. Okay? Now these numbers, again, 5/8 and 3/8 are the ones where the math actually works out, turns out. But people use their own numbers in here quite a bit. And what you do is that each time it does this, it takes all these midpoints, and then it averages down this vertex. Okay? So if you think of this as being a big hump like this, it averages down the vertices as we go and smooths. Okay? And this is one set where we get what we call a split and smooth. We first split, generate all the edge points, okay, in one step, and then we go back over the whole thing and we take all the original vertices and smooth them out a little bit. Okay? And then we split again, getting all these edge points, going back, taking all the vertices, smoothing them out again. And we get these really nice, smooth surfaces. Okay? Now these things pop. Now this is called loop subdivision. Okay? It's also used by Pixar somewhat because Charles Loop worked there. Okay? It is a fairly simple scheme that you can do with triangles. And triangles, you don't have to have all this god-awful data. Well, you have to have a pretty bad data structure to store them, because with a triangle data set, typically what we store with the triangle is we store pointers to the 3 vertices of a triangle. So we get these, store all the vertices in some array over here. Okay, and then we get pointers to the vertices here. And then we also get in here pointers to the next triangle. So a triangle here contains really 6 pointers. Okay, 3 to the vertices and 3 to the adjoining triangles. If the pointer's null, then there's no triangle, there's no adjoining triangle over there. Okay? And we can manage these. This tends to be a little less pointer hell for everybody. Okay? When you get going, although it's harder to, say, figure out how to work your way around these vertices in some order, or it's harder to work your way around a vertex, whereas in the other data structure we could do that. But here's one that works with triangles, and triangles are something that we use over and over again, and it was motivated a little bit by how we do things with a sphere. We constantly play with these geometric structures in our work. So this is subdivision surfaces. It's a natural extension of Chaikin's, right? What you did with Chaikin's. There's a lot of mathematics behind here, and I actually get to teach that course next quarter, and all the mathematics behind all this stuff. And it's actually pretty straightforward to do. So okay, next time I'm going to do, and I'm going to finish early today, next time I'm going to do shadows. Okay, and I'm going to go over shadow algorithms and show you how to do shadows. And I'm going to show you a little bit what we know about shadows, because it is still the stickiest problem that we have in computer graphics today, is how to do accurate shadows. It takes bloody well forever if you want to do them right? Or you can trade off and you can generate yourself what we call shadow polygons, and you can generate just an immense number of extra polygons in your scene, right, to generate shadows. Or you can do some really simple things by putting fuzzy spherical blobs down on the floor or something like that, and I'll show you how to do that too. That's actually pretty easy. So I'll do shadows next time, and we'll keep going. So don't forget discussion this week.